You are listening to the Think Brick Australia podcast. Think Brick Australia represents the clay, brick and paver manufacturers of Australia. Brick by brick, our podcast will discuss technical information and architectural case studies with special guests. I'm your host, Elizabeth McIntyre, the CEO of Think Brick Australia. On today's podcast, it's my great pleasure to introduce Mina Matta, who is one of our engineering interns, and he's actually going to talk to us a little bit about earthquake design and in particular, obviously, designing for masonry in earthquake regions. Welcome, Mina.
Hey, how you doing, Em? Thank you so much for having me on.
So what we're going to start with, Mina, is we're going to talk about what are the two governing standards that people need to think about when it comes to designing for earthquake regions.
So whenever we come to design anything in Australia, we have to refer to the National Construction Code. That details two standards as being deemed to satisfy or acceptable construction manuals for earthquake design. One of them is AS 1170.4. This lists all the general requirements for designing in earthquakes. And the other one is AS 3700. Which lists all the design requirements for masonry. But Section 10 of AS 3700 will actually detail earthquake design.
Okay, so we've got the National Construction Code and then we've got the Australian Standards 3700. All right, so then what are the provisions under the deemed to satisfy provisions? And maybe just before we go into that, what is deemed to satisfy? Just a reminder, what does that mean, Mina?
Deemed to satisfy is a specific provision within the NCC. And it means that you have satisfied the requirements, because within the NCC, what you have is you have performance requirements, and then you have the actual acceptable construction manuals. A deemed to satisfy provision means that using this manual, you have actually met the performance requirement.
Beautiful explanation. All right, so let's look at the provisions for AS 1170.4 for the factors for earthquake design. What do we have, Mina?
Yeah, so the first thing that you'd consider is the site hazard. So sections, for example, near Perth within lower Western Australia and sections within lower Victoria are more prone to actual earthquakes than other sections. And so with that being said, there's obviously a higher risk when you're building and you have to actually accommodate for that. And so based on these factors, you also have more design stringencies. So that's the first thing that we'd account for. We also account for what the building type is. So the importance level of the structure is governed under AS 1170. So for example, a standard structure that you and I would live in, it would be considered a type 2 structure. Because the loss of life that is actually caused by the failure of the structure would be something that is far less than an importance level 4 structure. Would be something like a hospital, something like an emergency shelter.
Right.
If that fails, there will be mass loss of life, and therefore we have to be a lot more stringent when it comes to that design.
Whereas type 2 normally sort of is relevant for like a house or something like that.
Applications. Okay. And so one thing that we actually do consider is also site subsoil classification. So these are ranged from A to E, where A is actually a very good strong site, a material or a subsoil that is very strong, almost similar to bedrock. And E is a very loose soil. And the way that we measure this is by what we call a standard penetration test. We get a standard, we drive it into the ground. We drive the first 150 mil into the ground. We ignore the values for that. We drive an extra 300 mils into the ground. And depending on the number of passes or the number of blows that are actually required to penetrate 300 mils below the 150 mil that we've already penetrated into, we'd actually be able to classify the subsoil conditions. So you have something like Class A would be roughly over 50 or even more blows, but you'd have something like Class E, which single digits passes. You'd have maybe 6 blows, and that would mean that you're building on a very loose soil.
Okay, so let's just take a moment here because there's a lot of information. So the first thing that we're looking at is the site of where the structure is going to be built. And you've identified some areas which you can find in AS 1170.4 of Australia that have got a higher probability that an earthquake's going to happen in that region. The next thing we're sort of thinking about is, okay, well, what structure are we building? If we're building a house, this is going to be a different consideration as to whether we're building a hospital.
Exactly.
And then the third thing now we're at to is we're looking at the subsoil classification. Now, this is ranked from A to E. A is very hard, and you were just saying then that under the test that we understand this works, that would take about 50 blows. Whereas if we look at E, very, very soft soil, that'd probably take only about 6 or something. What do they classify? Is sand? We don't build on sand?
So it's never only just sand. So it's always a mixture. And that's the problem whenever you're building on a job site. There's a lot of geotechnical considerations. And based on that, you'd have a soil with very different rigidity. So it could be a sand that's mixed with some fatty clays. It could be a sand with some silt with some fatty clays. And depending on that, you'd actually have to... This is why we do the test.
That's right.
Yeah.
Beautiful. All right. What's the other thing that we need to think about with the structure?
Yep. So the height of the structure is also a major concern.
Yep.
And one of the reasons that it is a major concern is because AS 1170.4, it gives provisions for the measurement of interstory drifts. And what that is imagine you have a diaphragm to diaphragm. So something like a slab. Let's say you have a tall structure, multiple floors. Let's say you're looking at a slab at the 3rd floor. The difference in horizontal movement between the 3rd and the 4th slab would be considered an interstory drift.
Right.
And why that's very important to actually limit is because we have something called P-delta effects. Whenever a structure ends up moving a little too much, eventually it will lead to collapse.
Yes.
You'll have an overturning moment causing collapse. So what 1170 says is that you should have a 1.5% maximum. So 1.5% of the height of the wall between your two diaphragms should be considered for the maximum deflection. But AS 3700 limits that further, and we'll talk about that in a second.
Okay. So what I'm understanding there is obviously when we're building something for 1 story versus 40, we've got to bring in some more sort of factors around earthquake design. So, Mina, now that we've talked around what the factors are, what are the design principles that people need to be aware of?
Yep. So one requirement is that the structure is tied together. What that means is that the roof and all the assembly, even the walls, all the forces that they are subject to will eventually be transferred again to the foundation. This principle of design is what we call monolithic design considerations, in that the whole structure acts as one. And that's really important because when you actually consider earthquakes, what we do end up seeing is that there's a lot of differential movement in the soil. And we have to make sure that everything remains rigid and acts as one. Otherwise, you have structural failure in the long term. And so what we have is that walls are actually required to be anchored to the roof. We see this in clay masonry all the time. What we have is we usually have a galvanized steel strip or a galvanized strip of sorts. It's attached to the actual rafter and it's tied down using a chemical anchor. And so the question then is, what is a chemical anchor? Let's say you have an epoxy of sorts, right? You have a resin that hardens, and what we do is we put the anchor into that.
Okay.
Yeah.
All right.
And it holds down the roof assembly.
So just before we move on to the next step, just recapping the design principles, the walls are required to be anchored to the roof, and you've talked around how we can do that with an anchor stud that's held to the masonry via a resin, and also what you previously spoke about, which is the provisions for the interstory drifts, which we've also discussed. All right, so just in summary, because we're nearly there, Mina, aren't we? Talk to me a little bit around mortar and the importance of mortar, and then around, I guess, the components of the masonry system.
Okay, so before when I detailed interstory drifts within AS 1170.4, we said that it's meant to be 1.5% of the actual vertical wall height. The actual height between diaphragms is roughly generally around 3 meters. And if we were to actually have that displacement, it would add up to 45 mil. Now, mortar is a very rigid building material. And so what happens is if you actually have a 45 mil displacement over that height, you're going to have a lot of cracking, a lot of cracks propagating, and you have eventual structural failure. So what AS 3700 does to accommodate for this is that it limits the interstory drifts further to a maximum of 10 mil deflection between the top and bottom of the diaphragm.
Mina, we talked a little bit before around the interstory drift.
Yep.
And it is limited. What's it limited to?
So generally it's 1.5% of the vertical wall height between diaphragms.
Yes.
So between slab and another slab, for example.
And then what is it the maximum in millimeters it gets to?
So generally you'd have a maximum height within a masonry wall of roughly 3 meters. That would be 45 mils if we're actually considering AS 1170.4. But whenever we're talking only masonry and the provisions within AS 3700, that is limited further to 10 millimeters.
And why is it limited further to 10 millimeters?
That is because if you consider the whole height of the wall to actually have 40 mil displacement, given that the mortar is a very rigid building material, you're going to have a lot of cracks propagating.
Yes.
And that's going to lead to eventual structural failure.
Right. And so that's really important. So we're only got a maximum of 10 mils, and this is really to prevent cracks coming in the building. What other things do we need to think about the seismic force resisting system? What are some other things?
The whole building and its components, they're designed such that it's either you have everything within the structure that is attached to it, capable of resisting the forces, or in the event of movement, they're almost detached in a way, in that any movement will not actually cause any additional loading on the structure. And so some of the things that we will consider is what I said before, the actual mechanical or chemical anchoring.
Yes.
That would be done to the actual top of the wall. We consider how the actual interfaces between the slabs or the different wall floors interact with the actual masonry. So for example, there's provisions within AS 3700, section 10, that actually account for inserting a slip joint using maybe 2 DPC materials in between a slab and the actual wall. And that actually allows for movement, but also helps the structure maintain monolithic action.
Wow, Mina, there's a lot of information that we've gone through today. Let me see whether I've got most of it under control here. The first thing that we need to think about if we're going to be designing in earthquake regions are the NCC lists AS 1170.4 is the deemed to satisfy construction manual, and we've gone through that, and AS 3700 is the standard governing general masonry design. So those are the two things we're going to look at. Before we even start designing in earthquake regions, we're going to look at where we are. We're going to try and see if there are particular areas throughout Australia that are prone to earthquakes, and that map can also be found in AS 1170.4. The next thing we're going to look at is what's happening underneath the ground that we're about to build on, and we've talked a little bit about subsoil classification and how it gets that classification, how it's rated based on the number of blows. And the other thing we've got to think about is the height of the structure, whether we're building a house or whether we're building a hospital. They're really important. When we're designing, we also need to think about how the walls need to be anchored to the roof. And then we've also talked about the interstory drifts and how much movement you can get from diaphragm to diaphragm. We also talked around the fact that this distance is normally 1.5% of the total story height, but we do limit that to a maximum of 10 millimeters. And the reason we do that is because we don't want our beautiful brick walls being cracked through the mortar, because as we know, mortar has quite a brittle nature. There's other components that you've gone through in terms of how we can make the structure seem monolithic and move together in an earthquake, so that it ensures that when you're designing for earthquake, the buildings are going to stay sound. Have I got everything, Mina?
That's pretty much it. Of course, this is only a very basic rundown because it does require a specialized engineer, but we have pretty much got to the gist of it. Yes.
And so, Mina, where do people go if they want to find more information about designing in earthquake areas?
Yes. So we have 2 options. We have TBA Manual 4 for brick masonry. If you're building for concrete masonry, you may refer to the MA55.
Well, Mina, I'm shook after that conversation, and let's hope that your buildings won't be shaking once you've followed these guidelines. We've got all the information in the show notes. Thank you so much for joining us. And remember, when you're thinking about earthquake design, think brick. If you have enjoyed this podcast, please follow, rate, and review our podcast. We are always looking for new ways to think brick. If you have an idea of what you'd like to hear about, there's a link in our show notes to let us know.